All right. Good afternoon, everyone. And so it's super exciting for us to see so many people at these final presentations. I'm Fabian Royer, one of the co-chair of the event, and Simon here is the other co-chair. So 5 days ago, 32 extremely bright students arrived at Caltech from all over the world. And here they are sitting among ourselves. They didn't know each other, but they shared the same passion for space exploration. And so we split them into two teams of 16, and they have been competing on a space mission concept over the past 5 days. So really exciting. And so today you are going to be able to see these two incredible mission concepts they came up with in only 5 days. So I keep stressing this, it's only 5 days. This is incredible. And so this year mission concept deals with landing on Enceladus, this moon of Saturn that has global ocean under its ice crust. And so I'll hand in the mic to Simon and give you more information about this afternoon.
Yeah, thank you, Fabian, and welcome also from my side. Before we move on and introduce the first team, I'd like to briefly let you know what happens this afternoon and then also introduce the jury because, as we said, this is a competition, and so the team's concept will be evaluated by a jury of experts who is here also with us. So I'm going to introduce them very briefly. I see they have all their binders in front, so I won't ask them to stand up, just wave so that people know who you are, and then at the end, when I introduce everybody, please welcome them with a warm round of applause. So the head of our jury is Tom Spilker. Tom is an independent space consultant and has a lot of experience working priorly at JPL. Then we have Steve Matusek, also JPL from the A team. We have Morgan Cable. Morgan is a research scientist at JPL and has a lot of experience on icy moons. Then we have Jackie Gish. Jackie is a visiting associate with the aerospace department here at Caltech and has worked at Northrop Grumman before. And then we also have Dave Murrow with us from Lockheed Martin. And Mike Tierney from Northrop Grumman on the very right from my side. All right, so please welcome them with a warm round of applause. We'll have now the two presentations. Each presentation is about 50 minutes. I'll ask you to not ask questions during the presentations. Please hold them for the end. And then at the end, we'll have roughly 10 minutes where you can ask the teams any questions you may have. After the first presentation, we take a short break so that the second team can get set up, or if you need to use the restroom, they're located here outside of this door. Yeah, that's everything I wanted to say. So with that, I'd like to welcome the first team, Team Voyager, to come on up and start the presentation. Please welcome them also with a warm round of applause.
Welcome everyone to this Caltech Space Challenge. Today we are going to present the mission concept developed by the Team Voyager. Okay. Thank you. For today, our mission is to reveal the unseen, to propose something that is going to revolutionize what we know about the universe and what we know about life. In particular, I want to start presenting my team, Team Voyager. We've been constantly working for this week, 24 hours per day. In particular, we have our science team, the engineering team, orbit person, the system engineering team that did a very nice work integrating all the other teams, and the management team that overviewed the entire project. Our mission, it's named Silenus. Why Silenus? In this case, as you can see, is a spectrometer investigating the livability of Enceladus with a network of underground seismographer. So this makes us a spoiler on what will be the concept we are going to propose. But why Silenus? Silenus in the Greek mythology was a companion of Dionysus, the god of wine. And it says, that's not certified, that he defeated the giant, one of the giants, and indeed Enceladus was the giant. How he defeated? It was with his spear. And you're going to see that we are going to try to reproduce and redo the same now. For what concerns the outline of this presentation, we will start with a why we are here, but actually why we want to propose this concept mission. Later we will go answering the question of how, so how the engineer can do and make this happen. At the very end, we will propose a strategy. So how, once the engineering define the plan, we can actually carry out the plan until the success of the mission. I think we can start with Erika Nathan from the team of science team, and in particular with the scientific purpose of the mission.
I'm going to tell you how Enceladus introduced itself to us. Or not.
It doesn't work.
Enceladus started as just a speck of light near Saturn. It wasn't until Voyager that we saw that this very small moon, just about the size of Arizona across, had a very bright young surface. And then Cassini told us that this moon is geologically alive. So to get you oriented, we're going to follow the water, and if we start at the core, working our way outward, the first place we encounter water is at the core-ocean interface. Here's a really interesting place because the core is probably relatively high porosity, meaning that lots of chemical interactions can occur and produce organics and salts. There may also be hydrothermal activity, but most importantly, the core is where a lot of the heat is dissipated in Enceladus. And this actually can drive circulation in the ocean and gets all of these chemicals that we produce to circulate through the ocean. Moving upward from the ocean, there's the ice shell. And between this is the ocean-ice shell interface, which is a really intriguing place to think about habitability because organics can pile up there. And in places like Antarctica here on Earth, we actually see that they're very rich environments. What's really cool though is the plumes of Enceladus that you all have just seen in the previous picture. And the way that this happens is water from the ocean is communicated through fissures in the tiger stripes, and those actually can communicate the material from the ocean up to the surface and out into space. The surface itself is really geologically young, relatively devoid of craters with lots of interesting tectonic features. And this is important because the radiation on the surface produces oxidants. And the fact that the surface is young means it could be recycling and providing a battery for life, where you can communicate materials out from the interior of Enceladus and then back in. And of course, there's the plumes themselves, which Cassini, even though it wasn't looking for habitability, was actually able to find salts and organic compounds when it flew through the plumes. And all of this makes Enceladus a really promising world for habitability. It of course has lots of water. It's an ocean world, it's a global ocean. There's energy from tidal dissipation, and as we just discussed, there's some really promising chemistry. But the key to habitability is getting all of these in the same place at the same time. Which brings us to our main overarching scientific question. Is or was there a habitable environment on Enceladus? We've split this up into 3 specific scientific objectives. 1, to characterize the organic chemistry of the plume ejecta. Secondly, to characterize the inorganic chemistry of the plume ejecta. And lastly, to constrain the age structure and exchange pathways of potential habitable environments. For each of these, we detailed our science traceability matrix. But don't worry, I don't want you to read this table with small text. This is to show you that for each one, we identified specific sub-questions, as well as the measurements we would need to answer those questions, and then the instruments and requirements that we would need to achieve this. But to summarize, I'm just going to go through and tell you which instruments we need to answer each of the broader objectives. So for the organic chemistry, we're going to need to fly through the plume of Enceladus using our mass spectrometer and our capillary electrophoresis system to measure the organic chemistry of the plume ejecta and characterize it far better than Cassini ever could. This will help us not only understand the chemistry of what's there, but also the structure of this, and look at important potential biomarkers. For the inorganic chemistry, we'll be able to use those same samples and our ion-selective electrodes to learn about the salinity and pH. This is really looking at what environment the organic materials are in for the ocean. And that's really important because on Earth, we know that salinity and pH can control where habitability is. And these are unknowns that the scientific community really needs to have resolved to characterize the habitability of Enceladus. And then, when we're talking about the age structure and exchange pathways, we'll be using our altimeter and gravity science instruments, as well as, on the surface, a context camera to look at stratigraphy, and most excitingly, our seismic network. So just to summarize our instruments, we have our orbiter payload and our surface payload. And these are some of the types of data products that we could get out. So we'll have really high resolution mass spectrometry that will tell us about the organics and seismic signals from Enceladus that can tell us about the interior structure and characterize things like what actually is the shape of the core, how much energy is being dissipated there. And these are all really important to constrain the chemical interactions there and the overall energy budget for the planet. So taking what we know from our science questions and what we need to get out of that, as well as our broad mission concept, we can combine that with what we know about the surface of Enceladus to select the best places to send our seismometers. One of our main goals with the seismometers is to actually get 3D structure of one of these fissures that communicate from the ocean to the surface. And so for that, we'll actually need a triangular arrangement of seismometers that includes one of these fissures. So for this, we've characterized the hazards, which include a scattering of ice blocks larger than the building we're in, as well as pinnacles of ice 140 meters tall, as well as pockets of CO2 that can outgas explosively. So the South Polar Terrain is not a nice place to go on vacation, but the science is there, so we're going to go. Another thing that's worth noting is that the resolution we have is not sufficient enough to characterize these hazards fully. So we've chosen our landing sites where we have the best resolution images from Cassini and with the lowest probability of hazards. But it definitely makes the job of the engineering team a little bit difficult since we're sending them into the unknown. So here are 3 sites in the South Pole. And then we're also going to have a seismometer in the north because we need these teleseismic distances. Basically, the seismometers need to be far enough apart that we can actually start to get some images of the core and know its size and other parameters like its density combined with other measurements that we're taking from orbit. To summarize, our mission is a win for science because we get habitability and so much more. Our habitability measurements will inform future missions targeting life detection, and our geophysical measurements will revolutionize the way we think about how icy moons evolve. More than that, we're getting a closer look at the surface than ever before, and it's going to spur so many new questions and research for decades to come. And with that, we need to get to Enceladus and achieve this mission. And to explain how to do that, it's my absolute pleasure to introduce Kati.
Thank you, Erica. So as she mentioned, I'm going to be covering the mission concept of how we're going to achieve this daunting task of achieving those science objectives. So as part of the challenge, we were given some constraints that we had to consider, and from past research of Enceladus, we have some information that we needed to also take into account in order to design this mission. The first one being an arrival period of time between the years 2036 and 2042. Now, this poses a slight problem that the climate on Enceladus is very dynamic in the sense that we'll be arriving in the dark if we don't make it in a short time window. And specifically, the regions that we're going to be targeting at around 70 degrees of altitude has that problem as well. The polar orbits that we're considering to look at the specific south polar region as well as that specific point on the north, we have some issues with station keeping there because of the requirement of a very large delta V. This could severely impact our budget in terms of fuel and as well as other factors which we'll look at a little bit later. Since we haven't had any surface measurements or images of specifically from a mission except for what Cassini took, the terrain is very unpredictable and unknown. And because of this, we don't know what we're getting into. So we've got to do some preemptive measures for that. The environment is also quite vast in the sense that temperatures can range anywhere from 30 to 50 Kelvin on the surface and up to 200 Kelvin within the plumes themselves. So this will then determine whether we're going to be doing in situ versus remote sensing measurements. And finally, this is a new Frontiers class mission, so we were told that it can only be a budget of $1 billion. And we realized how much of a task this would be as we got further into the week. So just before we go further, I'd like to do some trades to determine which of our, which possibility we're going to be using in our actual mission architecture. So we've considered various factors for the mission, such as orbit, travel time, architectures, as well as what kind of collection of data we'd be doing, so either in situ versus remote. So for the first one with orbit types, you could see that we have a polar halo orbit. We could do a flyby, which is what a lot of previous mission concepts have proposed, and a stable orbit. With the travel time, to get to Saturn, there are lots of delta V options, and it can range anywhere from 6 years to 10 years. And the choice that we would make would then determine how much of fuel we would need. Again, coming back to what our arrival period would be would then affect the time frames. And I'm just going to continue and move on to the final option, which is our system architectures. And this was a determining factor in what we were actually going to be doing for our mission concept. So we had to decide between an orbiter, a lander, a combination of both, and how many of each. And just with the color coding, you'll notice that with the trade-off study, the green is the most preferred option and would give us the optimal result. So coming back to the last topic we talked about with system architecture, we noticed that considering various things like operation of the instruments on payload and also the type of collection we'd be doing, so either remote or in situ, had various impacts on the different kinds of architectures. And considering 3 different options, we've decided to go with remote sensing focused, using an orbiter and small surface sensors. So this way we could get a bit of the science objectives and that way be within the constraints as well. So for the trajectory to get to Enceladus, we'll be using a series of gravity assists from Earth to Saturn to enter into the Saturnian system. And this will be using the EVEE And we'd be arriving in about 10 years, so there's a long journey to get there. We'd be doing multiple flybys to get there, like as previously mentioned, and we're hoping to conduct a polar halo orbit around Enceladus. So the Enceladus polar halo orbit has various dynamic factors that we need to consider with orbital mechanics, and just doing some computational work, we've determined that we will be doing 2 revolutions per Earth day for our science data collection. And also to remain within the actual orbit around Enceladus, we've also realized that we needed to do several corrections, and this is some other mathematical computations, and I don't want to bore the audience, so we'll just say that we've done it and we've accounted for it. And specifically with the various landing sites that was mentioned with the science overview, we can see here in the image with the pink trajectory line, we are covering very close to those landing sites to be able to get pretty accurate measurements. And here we just take a look more with the simulations that were performed to see whether the task of achieving with science data collection can be feasible or not. And just before we get to deorbiting, we were able to also consider something called planetary protection, which was one of the important things that was mentioned in a lot of NASA proposals after determining that Enceladus might be habitable. So for this, we considered various locations and kind of reflected a little bit on what Cassini did with how they crashed into Saturn. And we considered which one would conserve our delta V measurements. So we've decided to go crash into Tethys instead. And all right, well, more of a disposal, I guess. But we're just hoping, because we haven't fully understood the environment of Tethys, so we can't for sure say that it's habitable, but there's a likely chance that it would allow us to be conscious of planetary protection as well. So for the concept of operations, we begin from launch all the way to disposal, as we just recently saw in the previous slide. And it's going to take several years for the entire mission. But just as a quick overview, it'll take 10 years just to get to Saturn. And we're hoping that the actual data collection can be completed in about 1 year before doing the disposal. And the total mission is going to consist of about 14.5 years. And I'd like to then pass on to the next presenter, Kelsey, who's going to be looking more at the technical overview and engineering concepts.
Awesome, thank you. So on behalf of the engineering team, I would like to impart on you the information of how exactly we're going to achieve the science objectives that the science team has laid out for us. So to begin, I'm going to talk about the high-level architecture of our engineering solution, and this is a 2-part harmonious system. We have an orbiter, and we have 4 penetrators, which we've aptly named the Golden Girls. And we've found that this system architecture is the best possible for both cost and risk aversion in order to achieve our science objectives. So let's begin with the orbiter overview. So the orbiter can be thought of as the parent spacecraft. Within the orbiter, we'll be housing the 4 penetrators to get from Earth to Enceladus. In total, our first preliminary mass estimate is a total mass, dry mass, of 890 kilograms, with a max power production of 370 watts. Now, going into more detail into the subsystems, on a surface level, our orbiter will have mounting capabilities for our communication satellite between the actual orbiter and the deep space network. It will have the capability for our star sensors and sun trackers to be placed on the surface, as well as thrusters. Now, internally within our orbiter, we'll also house the remaining of the subsystems necessary. Now, this includes our onboard computer, payload instruments, as well as preloaded 4 penetrators. Now, I want to talk a little bit about our choice for solar panels. Enceladus is very, very far away. How are we possibly going to get 370 watts? And why did we choose this? Well, from trade studies, we found there were two options. We could go with RTGs, or we could go with solar panels. Now, upon going through a trade analysis, we found that a total solar array area of 134 meters squared will produce the necessary power to power all of our subsystems and gather our science data, and will be half the cost of an RTG. So we went this way. Now to talk a little bit about the technology readiness level. So our choice in technology readiness level of our subsystems is between around 8 and 9, and we really wanted to make sure that they were as high as possible. This is because 4 out of the 5 of the science instruments are going to be on board the orbiter. So this is absolutely critical for mission success, that we have flight heritage hardware that we can prove will work. So now I'm going to move on to our Golden Girl penetrator subsystem. So in total, we have a mass of 30 kilograms. The size of these penetrators are about 11 U, and the max power required to actually run everything on board our penetrator is 11 watts. So to talk a little bit about the subsystems and the technology readiness level, all 4 of the penetrators will be identical, but we require a lot of technological development in order to make sure that these will work. Now, there has been 2 mission concepts in which seismology utilizing a penetrator has been done in the past. This is on Mars and the Moon. However, there has not yet been a mission concept for penetration to be used on an icy moon for purposes of seismology. So this is why we have a lower TRL on this section. Additionally, what we have here is the reaction wheel system. So from trade-offs, we found that we couldn't really just huck out the penetrators and hope that they would properly align themselves into the icy moon, especially with the requirements of the seismometer orientation. And so we went with using a 4 reaction wheel, 3 for the axes and 1 for redundancy, in order to provide some form of attitude control such that we can have our seismometers actually work. Now, there has not yet been any reaction wheel usage that we know of for the usage of a penetrator into an icy moon. So this is why it's on the lower end of the scale. We know that reaction wheels have been used a lot in CubeSat missions. This is very common, but this technology has not yet been adapted to a penetrator. Now, the next instrument that we need to think about, of course, is power. How are we going to be powering our our penetrators, and why is this so low? Well, essentially, the power requirements and heating required, the commercial availability of the batteries we need is not yet there. But we presume that through technology development and the rapid ability of power systems, that it will be ready for the time of our flight. Now, I want to now talk a little bit about how exactly our penetrators and our orbiter are going to work together in order to achieve the science mission goals. So we understand that we're starting on Earth, and we want to get to Enceladus. So what we need to do first is enter the science-defined orbit, which Katie talked about a little bit, of Enceladus. So immediately, once we arrive at Enceladus, we will be releasing the 4 penetrators sequentially onto the surface. They can immediately begin to collect seismic data. The penetrators will have an onboard computer for storage. We've been told by science that they need at least 2 weeks of seismic data, so we can release them right away at the beginning of our mission, and they can passively be collecting data and not transmitting it upward to us. Now, while this is happening, we'll be flying through the plumes of Enceladus. Now, this is so that we can collect the necessary mass spectrometer measurements needed to determine the habitability of this icy moon. So while we are flying through the plumes, our seismometers are collecting data. Once we have had 10 flybys through the plumes, we should have enough data in order to move on to our next objective, which is to collect the seismic data, relay it back to Earth, and then we will go back into a more stable orbit to do laser altimetry. This is really where our mission lifetime of about a year occurs. We can get our science data from the plumes within 10 passes, and we can get our seismic data within about 2 weeks, but the laser altimetry requires much longer timescales, and because of our more stable orbit taking a longer time, this is where we get our 1 year mission lifetime. So with that, I've introduced a little bit about the engineering that we hope will be used to satisfy our mission requirements, but how exactly is this development and budget going to work? So I'll pass it back to Katsi, who will be discussing this.
All right, so just as a preview of this section, our team had very ambitious architectures, and this was the reason why we ended up shooting down a lot of them, and there were a lot of iterations that happened in order to stick within our development and budgeting. So we were told that this is a New Frontiers class missions, and we were given $1 billion. And up until 2 days ago, we were under the impression that we were also going to need to account for launch operations and just general operations costs as well. And luckily, the organizers were able to take that away, so we didn't have to use that anymore. But also, just looking at the operations from the ground level, we will be using the Deep Space Network, and we'll be using 2 different kinds of bands, one for station keeping of the spacecraft and one for actually transmitting and receiving the science data. And given the $1 billion budget, as most people know, with space missions, you have to set aside some contingency. And with the proposals with NASA, we followed the similar technique of setting aside 30%. Because this is an outer planet mission, we're going to go ahead with looking at the various subsystems or systems that need individual allotment. So the individual things, as can be seen in the table, have various allotments that are being done using anonymized past missions as well as historical data. We've then decided to go ahead and also look at specifics such as the flight systems and the science as well as payload, which we'll be covering a little bit later. Just to mention, we were able to achieve our budget. We actually had some excess from certain sections that we were able to pass along to others. So we'll look at that as well. So specifically with the flight system, which is everything for the orbiter and the 4 penetrators, we're looking at various systems on board the flight vehicle. Obviously, the systems engineering / project management takes up a large section of it, and we know that this is required for planning of various technical reasons, making drawings, engineering decisions, as well as the integrated assembly and testing. This is also pre-launch, so it would be phases A through D. Some of the other components that we've looked at are the telemetry, tracking and command, attitude control, and power. So initially we were thinking of using RTGs as well, but noticing that the costs of each RTG is skyrockets, like we decided to go ahead with the solar panels. And luckily enough, we were able to get some excess budgeting from our science instruments, and science was kind enough to give that to our power system in order to meet our science objective. So there are various risks that we have to analyze for this mission as well, and we can separate them into 3: cost, scheduling, and technical. So with technical, we're going to look at a different kind. So if we were to differentiate between the orbiter and the penetrators, there are various component risks. So any specific system failing, how would that affect our overall mission, and how can we recover from that? So one example would be if our solar panel was damaged as it was flying through a plume and colliding with plume ejecta, what would the impact be, and what would the risk factor be for that? And on the penetrator side, if we're not able to get it aligned so that the seismometer is inside the ice, we wouldn't be able to measure the tomography, which is again one of our science objectives. So if we were just to look at science-focused risks, there are various possibilities. And here in this matrix, you can see there are various science values that have been normalized for failures at various steps. So something like an altimeter failure all the way up to failure of all the penetrators and how this would affect our mission. So you can see that the value of risk with just a sample failure, so for example, if the orbiter were to fail, is a lot lower than a failure in the northern latitudes. So as we said earlier, the timeline for this mission is about 14.5 years. And if we were to consider every phase for this mission from pre-A to F, it would take almost 23 years. And this is just to account for all the various developments required for technology, designing, testing, operations, because there's a lot of manpower that's required once we launch for those 10 years. And there are various critical events that people have to constantly be monitoring in case something goes wrong and we can save the mission. And just with the work breakdown structure here, you could see this just at a first preliminary level. But there are, again, various systems that are going to be involved with this. And specifically with mission systems, there need to be people that are tracking and monitoring the penetrators, the orbiter, and the ground system, so that the data received from all of that science collection is then going to be analyzed properly and used for future reasons. So our public outreach is to get space accessible for everyone. Usually with space technology and space missions, the most people that are involved are STEM related. And with NASA's current objectives to try to get non-STEM people involved, we have various things, like up on top you see the fashion show, and they're trying to get also a lot of virtual reality, artistic impressions from the public, just to have them involved, inspire them, and engage them, and not just think that science is out there for us people like scientists, engineers, but it's really out there for everyone who's interested and is a space enthusiast. So I'd like to pass it back to our lead, Lofty.
Thank you. So I think it's time to wrap up the mission concept that we have presented. In particular, we don't have to forget that we have some precise science objective. That's the most important part. That's why we are here. We want to perform science, we want to perform research. And to do this, we have to take some risk. We have to take a step forward. In particular, in this case, our science objective want to characterize organic and inorganic chemistry on a really far planet. But at the same time, also constrain the age, the structure, knowing as much as more information we can. How we do that? We do thanks to a spacecraft and a penetrator, as has been illustrated in our mission concept. In particular, as a timeline, this journey, because it is a research journey, it will take a lot. It will take a lot of challenge, and of course, we are ready to face each of them. To face each of them, we will start, of course, with what takes us to arrive to Enceladus. And at this point, we don't know what we are going to face. And I think this is a part of the main challenge. So in particular, what we want to do, we will reveal what is unseen. I would like to thank everyone for being here, in particular in my team, which I will ask to join here, and we are open for any question regarding our mission. Thanks.
All right, thank you, Team Voyager. Are there any questions from the jury? We will start with the jury first, and then we'll see if we have time.
So thanks. I guess the first thing I want to say is you guys did a great job. Lots of work, lots of hard work. Great, very cogent, understandable presentation. So thank you very much for that. We all have questions, so I'm only going to ask my one. And it's a timeline question. It's a mission ops kind of question. So can you explain to me a little bit more what the sequence is between getting to Enceladus and doing the plume flybys and dropping off the penetrators? And the reason I ask is really because I sensed, or I saw, an inconsistency maybe between what you gave us in the fact sheet and what we saw presented here. So maybe it's a science question, because it seems like why and when those penetrators go down are pretty important from a science point of view. So that's the question.
I can answer that question. So with the timeline, we'll pull it up here. So to get to Saturn, obviously, is the 10 years, and then once we're in Saturn insertion orbit, we begin to spiral down to enter Enceladus. Once we get there, we'll then be at our polar halo orbit. Now, that's not a very stable orbit, and takes a lot of delta V to maintain, so we want to minimize the time there. As soon as we enter, we'll begin doing our plume sample passes, and by the end of that, we then actually deploy our seismometers at the end of that period. And so near the end of the orbit, we'll deploy the 3 seismometers that we want in the south polar terrain, and then following that, we transfer out of that polar halo orbit into a more stable periodic orbit, which is at a little bit lower altitude, and then from there, we deploy our 4th seismometer. Now, it's important to remember that this one cannot really be deployed from the SPT orbit, just because of the inclination, so we have to first do those 3 right at the end of that halo orbit, and then deploy the last seismometer once we transition out of that, and then begin the seismic measurements for that period. And that will take, of course, the 2 weeks, and then the rest of the terrain mapping will occur using the stable periodic orbit for roughly a year.
Excellent presentation, guys. This is really exciting stuff. So I want to ask a little bit more in terms of detail about the instruments. So I noticed that you mentioned you're having a mass spectrometer and also capillary electrophoresis. Are those discrete instruments, or are they one unit? You also mentioned ion selective electrodes. So are these integrated into one single package, or are they separate? And what is the front end?
So the package is, the entry sample processing unit is attached to the capillary electrophoresis front end, and capillary electrophoresis can actually pass into the mass spectrometer. That's a common way of attaching it. We use the design that was proposed for the Pisces instrument. And the advantage of it is that it doesn't do any destructive operations on the organics before they reach the mass spectrometer. So it's intended for coupled measurements for mass spectrometer combined with capillary electrophoresis, which can tell you identification of, like, for example, specific amino acids or chirality identification. And the ion-specific electrodes, it's intended to be a different mode, because we have sample collection, it enters the front end of Pisces, and then it goes into these ion-selective electrodes unit, which is fairly minimal. It's essentially 4 total electrodes, and there's a bit of technology development that's going on for that in terms of miniaturizing those, because we're taking essentially the Phoenix, the wet chemistry laboratory onboard Phoenix, and we're breaking it apart, essentially, just to get at the pieces and attaching that to ours.
All right, this is great. I understand this a little bit better. So you're flying through at what altitude for this part of the collection? 30 kilometers. Okay, so that's technically not at the point where the individual jets form a single plume. So your trajectory is going to have to be dead on in terms of hitting some place that has grains. Well, let's say you do that. All right, and how exactly are you going to grab the grains and plop them into the capillary electrophoresis instrument?
Sure, we were planning to use the same approach of Cassini, which was the open source opposing the RAM direction in order to maximize collection. We're also evaluating the possibility of aerogel, as capillary electrophoresis can work on a aerogel sample. There's current development on that at JPL.
Okay, one final question. What's the velocity that you're doing this at?
150 meters per second, but we can vary because we have a different orbit design, as has been shown. we select one of that based on some trade-off also with the stability, but you have a possibility also to go at 1 kilometer. There are different halo orbit that you can basically design.
Okay, thank you.
If I can add, the relative velocity is mostly given by the plume velocity itself, not from the space velocity.
You mean at a
The
kilometer
eject
a second?
velocity.
That's not actually, at 150 meters per second, that would be a true statement. There's about an order of magnitude between.
It also varies with the size of the particles. Very large
Yeah.
particles are going very fast.
But they only had a week, huh?
So this is a data sufficiency question. It was unclear to me when you talked about the 3D structure of at least one fissure. You talked about where you're putting your penetrators and how long they're on the surface. Can you describe that a little bit more to me about how is the data you collect from that sufficient for the science that you want to get back from that?
So the key with having the 3 seismometers in the south polar terrain is that you really need ray crossing to get at the 3D structure. So when you have source signals coming into your seismometers, if you have 3, you can actually triangulate between them and use tomography. It would be low resolution compared to what we do here on Earth because, of course, this is a very small seismic network. But compared to no seismometers, it's a lot of information. And we would need to have a lot of events to do this well. But the good news is Enceladus has that. So we know that the fissures are opening and closing in response to tidal forces. And so over the course of 2 weeks, we would have a lot of those since the tides occur. We have diurnal signals. There's also, because there's an ocean and ice shell, we'll always have ambient noise that we can use. And so we'll have that background signal and we can do autocorrelation of the noise to get back to the tomographic and actually get some resolution on the width of that conduit at depth.
I would like to follow on with that. So we are using UHF antennas and transponders on the penetrator, and there's transceivers on the orbiter, which transmits the data from. So there's no two-way link, but just a one-way link from the penetrators to the orbiter.
So can I ask one quick follow-up question? So how many penetrators have to work to return the science that you want to get?
So that's been explored in our science return risk evaluation. And of course, if you want to get full science from this, you want all of them to work. The key is some of the information we only actually need part of our network to work. If we have even one seismometer on the surface, we're already going to be learning a tremendous amount about the depth of the seismic signal, which can tell us where the brittle ductile transition is occurring. We can also, with just 2 seismometers on either side of Enceladus, get all the information we need about the core. With 2, you could have very poor constraints on the fissure, possibly depending on which 2 it is and the ray crossing paths. And then you really do need 3 to get the tomography, but that's one part of our objectives. So if the seismometers fail, all of them, we still achieve more than 75% of our science goals.
We noticed that some of your TRLs are pretty low. Is any of your costs for improving those TRLs in your cost model?
Yeah, so you actually talked about the specific reason why we actually had contingency. So for any technologies that we're using that have low readiness levels, we are allocating more of our reserves towards that for various reasons, such as just a trade-off between off-the-shelf components versus customizing and developing something. It will take time, and we're hoping that futuristic technology would be ready by the time we're launching, since there is almost a decade between now and then. So anything with that's ready to go now, which has been used either on Cassini or any other deep space mission, we believe we will have less of a contingency reserved for that.
All right, we'll take maybe 1 or 2 more questions because we are pretty constrained in time.
this is kind of follow-up for the previous two topics. The first on the landers, the penetrators, I noticed that they stopped conveniently with the antenna still above the local environment. It may be that that is a very fluffy environment. There's a whole lot of porosity to that material. It may penetrate very deeply. How deeply can you go and still communicate? And then the other one is when you're proposing technology developments, NASA will usually say, okay, what if your technology development fails? What is your backup technology that will allow you to do this? It may cost more and you'll dig into your reserves, but you'll have a backup technology that will do this. If there's no backup technology, then it's an enabling technology and you have to foot all of the development costs.
So I can answer at least part of this question. I'll start with the backup options. We actually considered far more instruments than we talked about in the science instrument section, and that included several descoping options. For example, with the seismometers, we were also looking at doing ground penetrating radar. We would lose the information about the core, except possibly with some really creative radio science and altimetry, so there's still a chance. But really, what we would get is still most of the information, and that's a more tested technology. We had similar backup options for all of our instruments. And then about the antenna?
Yeah, so we can communicate up to 400 meters deep, but we included it as a risk factor. If it goes too deep or it just lands in an opposite direction, we lose the penetrator and we don't lose the data.
I think I saw on the on one of the charts that you were saying that it could get as cold as 30 Kelvin. And when you have a lander at that temperature and you're trying to get your electronics to work, you're obviously going to be stressing your batteries to maintain temperature. Could someone just talk about how you sized your batteries and how that would work?
Yes, actually, that's a really great question because that kept us up all night. And so Enceladus is a really, really cold environment, especially during the winter time. And yeah, we're talking about 30 Kelvin. So what we are proposing actually is to use a pretty good layer of aerogel in order to keep everything very warm due to its fantastic insulative properties. We know, so that's why we rated it as higher TRL because it has been used on Sojourner before. Now Mars is not as cold. We are then we sized our batteries with the heater power in mind. So this was the most important thing. And then around that, we decided, okay, we need to make sure everything is warm. Then we need to make sure we have the power. And then from then, we were like flowing the rest of the requirements. Does that answer your question? Very good.
Dave's about to bust buttons here, so let's get him.
Two final questions, and then we are.
Okay, this one may be easy, may be hard. Good job on the cost estimation. Oh, I got to go faster. So, is your contingency already? It sounded like your contingency, that 30%, is already budgeted for some things like technology development. So, is it really contingency, or is it just already used up? And what's your plan if it's all used up and there's unknowns?
So we actually, so what we showed you on the pie graph was just based on anonymized historical data, but we had cross-checks for every subsystem by either mass or weight or power generation. And when we did it both ways, we found that we were always getting a slightly lower value than the allocated amount for each subsystem or each division in the mission. So we found that if there were possible increases in pricing, we'd have not only that excess, but we'd also have the extra 30% reserves. And I mean, there is the possibility that we could totally blow our budget and it could go way over with technology development. But we're hoping that with convincing our, I guess, the proposal committee that we are able to achieve our scientific objectives and this would be a breakthrough for the future, they'd be willing to give us more money if needed. Yeah.
Commend you for your honesty. And Morgan is about to bust her buttons.
Okay, last but not least. So, given NASA's, limited financial resources and the fact that there are many amazing places to visit in the solar system, let's assume that this is going to be the only mission that will go to Enceladus, in certainly our lifetime, probably yours too. Some would argue that Cassini has already established that Enceladus is habitable. So why would I pick your mission if you're not specifically looking for life?
Well, as you can probably tell from the reaction in the room and the smile on my face, that is an excellent question. So Cassini did have several promising results that got it up to a habitability level. But if you actually look at NASA's Roadmaps to Ocean Worlds working group within the Outer Planets Assessment Group, which I helped write, then you'll notice that they have 6 different steps for where an ocean world is on its habitability matrix. And Enceladus is fully up to the last 2. It's habitability and then life detection. And there's the shaded region on that chart that I'm sure you know very well that says we have some evidence, but we're not there yet. And with this cost cap, life detection is outside the scope, and we want to make sure that our null result is interesting. So if there is no life, if it's not habitable, if that's the result we find with this mission, it's not a boring result. Like, we all want to find life, we all want to find habitability, but we're going to actually understand so much about the geophysics and about why Enceladus wouldn't be habitable then, because so far it's shown really promising signs. So our mission not only guarantees amazing success if it succeeds and we get the result we want, but if we don't get that result, it's still a wealth of scientific information that will revolutionize our thinking of habitability and icy moons as a whole.
That was a good answer.